Hey everybody, this is going to be the tutorial video for section 12.4 on angles and segment lengths in circles. So I'm going to switch my screen over. Where's the button? Oh, present now. All right. Okay. So section 12.4 is kind of split up into two parts. The first half of this section is going to be dealing with arc measures and angle measures. And the second half of this section is going to be dealing with lengths of chords, lengths of tangent segments, and lengths of what we're going to talk about called secant segments. So it's kind of a two-part lesson, but I'm going to do this in one video. So I'll give you a clue once the second half of the lesson is going to begin, and we'll kind of switch gears. So the first thing we want to look at is angle relationships in circles, and this is going to be related to the arc measures. We've been doing this in section 12.3 and 12.2, honestly, as well, by looking at those inscribed angles, those central angles, and those tangent chord angles. We're just going to expand on that a little bit today as well, and we're going to look at how to measure angles and arcs that are inside the circle and outside the circle as well. So I have a little chart we're going to fill out. I've also made you a nice organized chart that I've posted in the Google Doc and on my website. You are welcome to use that while you're studying for this chapter. I think it's pretty helpful. I've given you some visual aids. I've given you a nice place that organizes the formulas, so definitely take a look at that. But we're going to write it in together as well. I always find it helpful to write things down so that they get into my brain quicker. So the first thing, angles and arcs that intercept these circles have different relationships depending on where the vertex of the angle is located. A lot of these diagrams get real funky. There's chords intersecting, there's tangents intersecting, and what can be confusing is how the heck am I supposed to find where are these angle measures, what are these arc measures? And it's really about the location of the vertex of the angle. Look for where the vertex is located. It's either going to be at the center of the circle, it's going to be on the circle, it might be inside the circle but not at the center, or maybe the vertex is even outside the circle completely. And 3 and 4 are going to be the new ones for us today. I'm just going to give you some reminders on 1 and 2. So if your vertex is at the center of the circle, we've already seen this is what's called a central angle. And if you have a central angle, I'm going to draw the diagram first. Here's your center. Anytime you see that thick dot in the middle, you can assume that's the center. Let's just say I have 2 radii coming out from there. And let's say that this intercepted arc is 50 degrees. If you remember, whatever that arc measure is the same as whatever that central angle is. So it's going to also be 50 degrees. So capital A is going to be the measure of the angle. Let's call it A. Well, then the angle measure is just going to equal the arc measure. Okay, that's it. If your vertex is on the circle, meaning on the circumference, okay, it could be an inscribed angle, or it could be like a tangent chord we saw as well. So I'm just going to write inscribed angle, or it could be a tangent and a chord. Then whatever this intercepted arc is, say this is 100 degrees, it's not equal to the angle measure, it's 2 times as big. So in order to go backwards and get the angle measure, you got to cut this in half. So this would be a 50-degree angle. So this is going to be 1/2 the arc measure. So then the new ones for today, what if we get an angle that's inside the circle, but its vertex is not at the center? So I'll give you an example of what I mean by that. Let's say here's the center of the circle, but let's say that the angle we're interested in measuring is over here. So let's say I want to measure this angle in blue right here. Okay. And I don't know, let's say that this is a 60-degree arc, and let's say this is an 80-degree arc. We can find the measure of this angle based on those 2 intercepted arcs for those vertical angles. If I have information about these 2 arcs, I can find that angle measure, and here's how I do it. All I do is I average those 2 arcs, which means I'm going to take the big arc plus the small arc, and you could think of it as dividing that sum by 2 or multiplying that whole sum by a half. It's like the average of the two arcs. So just think of it as arc plus arc divided by 2. Okay? You just average the two arcs together. So all I'm going to do to get this angle measured in blue, which would also be this one because they're vertical, take the one arc that's intercepted, add it to the other arc that's intercepted, so these two crisscrossed arcs, and then divide by 2. And so I get 140 divided by 2, which tells me that that angle in blue would be a 70-degree angle. So you can't just say it's equal to the arc measure like you could if that vertex was at the center. The vertex now is right here where this green dot is at, and that green dot is not the center. So that's if the vertex is inside the circle. You add the two arcs that are intercepted and you divide by 2. If the vertex is outside the circle, it's very similar. And this could be two segments that intersect the circle twice. It could be two tangent segments, or it could be a tangent and a segment that hits it twice. I'm just going to go with a picture where it hits it twice. So let's say that I know this arc, which I'm going to call the outer arc. Let's say that's 100 degrees. And let's say I also know this inner arc between the segments is 60 degrees. If I want to find this angle out here in red, notice the vertex of the angle, I'm going to do it with a thick black dot, that is outside the circle this time. Okay? Instead of adding up the two arcs and dividing by 2, the only difference I'm going to do this time is I'm going to take half the difference. I'm going to subtract them instead. So it's going to be 1/2 the big arc minus the small arc. And we're always looking at the arc measures that are in between the segments. Okay? We're not looking at this one and we're not looking at this one. We're looking at the ones highlighted in yellow. So just think of this as big minus small, just dividing it by 2. The only difference from the inside the circle and outside is this one's addition and this one is subtraction. Okay? So for the one I just made up, all I would do to get this red angle on the outside is I would take the outer arc, the bigger one, which is 100 degrees. I would subtract the inner one, which is 60 degrees, the smaller one, and think of it as dividing it by 2 or multiplying it out front by a half. Same thing. This would be 40 divided by 2, which is a 20-degree angle. So this angle on the outside here would be 20. You have a couple more formulas to add into your toolbox. And again, I put these in a little chart for you online that I posted to make things easier. So really, though, again, the most important thing from this top box is it's all about the location of the vertex. If you can spot where the vertex is at, that's going to help you decide what formula to use. So let's try it. Down here, we got a couple examples. I'm going to erase some of these dots. If I look at the first one, we want to find the arc measure. I'm going to highlight it in yellow. So that's X, that's what we want. And they actually give us a 93-degree angle. So the first thing I do is I look at the location of the vertex of that angle. And if I look at the location of that vertex, I notice the red dot in the middle is the center. So my angle is inside the circle, but its vertex is not at the center. If I look back at my box, inside the circle, not at the center, means I'm going to add those two intercepted arcs and I'm going to divide by 2. One of the intercepted arcs is 109, and the other one is the X that I'm looking for. So if I add those up and divide by 2, it should come out to 93. So I'm going to set this up equation style. One arc that's intercepted is X. The other one that's intercepted is 109. If I divide those by 2, so again, the arcs I'm looking at are the ones intercepted by the green radii, or not radii, the green segments and the red segments. This one plus this one divided by 2 needs to equal that 93-degree angle. And so to solve this, what I do, I want to get rid of the fraction first. Think of it as like imaginary parentheses in the numerator. You can't touch the top until you get rid of that fraction on the bottom. I'm going to multiply both sides by 2. You get X plus 109 equals 93. Oh, times 2. So 186. Let me fix that. Whatever you do to one side, you got to do to the other. this would be 186. And then if I subtract 109 from both sides, that missing arc measure ends up being 77. Okay. So sometimes the angle might be missing, sometimes the arc might be missing. Regardless, you're just going to use that formula and plug in the information they give you. There will be one unknown. So what did I use for this one? I'm also going to make note of where the vertex was at. In this one, the vertex was inside the circle, but not at the center. Okay, the next one. I need to find this missing arc measure, so I'm going to highlight it. We got a missing arc. I look for where the angle is at. They give me an 88-degree angle right here, and the vertex of that angle is outside the circle. So this one I'm going to label outside. So I'm going to use the last formula. I'm going to subtract the arcs, and I'm going to divide by 2. I don't know the smaller arc, but I do know that the bigger one right here in green, that's 225. So here's my big arc. Here's my small arc. I'm going to set this up. If I take half the difference of those two arcs, 1/2 of big arc minus small arc, that should come out to the angle that I have on the outside, which is 88. So now I plug in. 1/2, the big arc is 225, minus the small arc that's in between these two segments is x, and that should come out to 88 on the outside. Kind of like I did last time. Here I wrote it as divided by 2. Here I wrote it as a half. It's the same thing. I'm going to multiply both sides by 2 just to get rid of the fraction. So I get 225 minus x equals 176. I'm going to subtract 225 from both sides. So negative x, remember to carry down that negative sign, is going to be negative 49, which means if you divide by negative 1, that missing arc measure ends up being 49 degrees. So this missing arc in the circle is 49. And again, how did I know to use that formula? Because I located where the vertex was at. I saw the vertex was outside the circle. Here I saw the vertex was inside the circle. And again, if it was on the circle, then I would just use what we did in section 12.3, or if it was at the center. Okay, the last one we have over here. This one's made up of 2 tangent segments because they only intersect the circle one time. Okay. Well, this one's interesting because we're trying to find the inner arc, x, but you'll notice they don't even give you the outer arc. I'm going to label that one in pink. This one has no expression at all. They don't give us a value for that. The only thing they tell us in this problem is that this angle out here is 84. So the first thing I do is I look for the location of that vertex. There's where the angle rays are stemming from. So there's my vertex. It's outside the circle, which means I'm going to use the exact same formula that I did right here. Okay. I know 1/2, the big arc in pink, minus the small arc in yellow, needs to come out to that angle measure, which is 84. Now here's the issue. I don't have an expression for the pink, and I don't want to call it y, because if I call it y, then all I'm going to have here is y minus x. And how can I solve one equation that has 2 different letters? That doesn't make sense. You're not going to get anywhere if you do that. So I don't want to call this y. Instead, what I want to think about is, what do all of the degrees in the circle have to add up to? How many degrees are in a full circle? Which is 360. But I've already used up x in this yellow arc. So if the whole thing is 360, and I've already used up x in yellow, then what's left in pink is going to be 360 minus the x that I've already used. So now I've gotten around having to use 2 letters by just using 1 letter. All I see is the letter x, which means I can solve. So my big arc, instead of calling it y, I know it's 360 minus the yellow arc, x. So this one right here, that's the big one, 360 minus x. And the small one is the yellow one, which we already had labeled, x. And I subtract them because there's a minus sign in my formula. So maybe I'm going to color code this so you can see what each piece is. Okay. Here's the pink one, that's big. And then here's the small one, that's in yellow. That way at least it helps you organize what each piece is in the formula. Go back to blue. This should equal 84. So now if I do the inside, I get 360. They don't cancel because they're both negative. Minus 2x equals 84. Now I'm going to do my trick that I did in the last one. I'm going to get rid of the fraction, so I'm going to multiply both sides here by 2. So then I get 360 minus 2x equals 168. Move the 360 over. Negative 2x equals negative 192. And then we just divide both sides by negative 2. So this one should be 96. Okay. That's pretty much how those work. And you're going to see some problems where there's segments that are overlapping. But it really is all about looking at the location of the vertex. This one was outside also. We found this angle measure was 96. All right, so now we're going to switch gears. So that's kind of it for, at least for right now, on angle measures and arc measures. I want to switch gears, and I want to look at the Power Rangers. Okay, why do I have pictures of Power Rangers? Because we're going to be talking about something called the power theorems. These theorems that we're going to talk about on this page are completely related to segment lengths. They have nothing to do with angle measures and arc measures anymore. We're looking at lengths of segments. That could be chords, that could be tangents, or it could be what we call secants. We've talked about all of these terms except secant, so I just want to tell you what a secant is. A secant is just a segment that starts outside the circle and it intersects the circle twice. Okay? So this segment that I have here in yellow is what we call a secant, and typically it'll keep going. It'll like continue. But a secant, I'm just going to write it over here, intersects the circle twice. And we don't care about what it does after it hits the circle the second time. We always stop it at this point, and that's all we care about. So when we're measuring these, we're only going to be concerned about the part that goes up to the blue dot. Intersects the circle twice. Remember, a tangent only intersects the circle once, and then it keeps going. And a chord is completely inside the circle. It has both endpoints on the circle. And so these relationships we're going to look at are what are called the power theorems, or sometimes they're called the product theorems. And there are ways to be able to measure how long a chord is, how long a tangent is, or how long a secant is. It has nothing to do with the angle measure or the arc measure. And so we have three big ones, and there's a Power Ranger here to represent each one. We have what's called the chord-chord power theorem. This is when you're dealing with two chords inside of a circle that intersect. Maybe I'll color code it with the Power Rangers. Blue. The red power theorem is the tangent-secant power theorem. This is going to be when you're dealing with a tangent segment and a secant segment. And the third one is called the secant-secant power theorem. This is when you're dealing with two secant segments, two different segments that intersect the circle twice. What does each one say? If I have the chord-chord power theorem, notice in the diagram you have two chords that are intersecting the circle. You got this one in blue, and you got this one in red. So we got BD and we got AC. And typically what these problems will do is one of the pieces of the chord will be missing and you have to find it. And all the theorem says, let me label these. Call this X, let me do red. Say this is X, AE is X, EC is Y. Let's say that BE is A and ED is B. Okay. All it says is if you take the two pieces that are in red and multiply them together, it's going to equal the two pieces in blue multiplied together. So if I take X times Y, it's going to equal A times B. So really, the two pieces in red multiplied together equal the two pieces in blue multiplied together. That's it. If you want to actually use the letters in the problem, AE times EC, the product of those two segments, equals the product of the other two segments, BE times ED. Okay. That's the chord-chord power theorem. You need to have two chords in order to use that, which means they have to be completely inside the circle. They can't continue onward. All right, the next one is called the secant-secant power theorem, or product theorem. In order to use this one, you have to have two secant segments, which means they have to intersect the circle twice and they have to start outside the circle. Okay. So if I look at my diagram, I'm going to label one of my secants in yellow. So CA would be a secant segment, and the other one I'll do in blue. A little bit of green overlap. CE is my other secant segment. And here's how I think about this one. This is the whole secant segment. I'm going to label that whole. And the way that the property is going to work is we're also going to be concerned with just the part that's outside, which means the part that starts out here at C and stops once it hits the circle the first time. I'm going to call that outside. I'm going to call that outside. And when I'm talking about whole and outside, I mean length, like the whole length of the whole secant versus the length of only the outside part, the part that's not in the circle at all. And what this theorem says is that the whole piece of one secant times its outer part is equal to the whole other secant times its outer part. So think of it as whole times outside of one secant equals the whole length times the outside of the other secant. So this would be for one of them, call it secant 1. And this one would be for secant 2. And then the last one, what if it's one secant and one tangent? So one segment hits the circle twice and the other one only hits the circle once. Okay. So the secant I'll do in yellow. Here's my secant segment, BD. Hits the circle at 2 points. Hits at C, hits at D. And the other one I'll do blue again. My tangent segment will be in blue. So tangent in blue, secant in yellow. You'll know it's a tangent. It only hits the circle once. Okay. And they don't draw the rest of it, but if it were to continue, it would just keep going outside the circle. It would not continue inside. This one's real similar. I'm still going to label this yellow one the whole length of that secant. And I'm going to label the part that stops at C. This is just the outside part. So outside. Okay, so one part of this equation is still just going to be whole times outside. That's going to be for the secant. But for the tangent segment, the length of the whole piece and the length of the outside piece, I mean, it's the same thing. So really, I'm just going to call this piece the tangent. Whole times outside would just turn into the tangent piece squared, because they're the same. So in words, what's going on? The length of the whole secant times its outer part, outside, equals the length of that tangent piece squared. Okay, make sure you square it, that's important. So that's what we use when we have a secant and a tangent. Okay, so you got to identify what the pieces are first. You have two secants, one secant and a tangent, or two chords. That's going to help you decide which formula to use. And again, I'm going to make a note. I would suggest you write this. These help with segment lengths, not arc or angle measures. If you're talking arc or angle measures, you got to use the stuff on the front. If you're talking about segment length, then you want to use one of these three power theorems. Okay, so how do we apply these? I have a lot of formulas and stuff written. It might seem kind of confusing. I'm just going to show you how they work. I got one example of each one. In the first one, it says R is a midpoint of TG, IR is 4, EI is 20, and TR we have to find. So first thing I identify is which power theorem am I going to use? I know that I'm trying to find a length. I'm trying to find TR. So I'm going to label that in blue. I'm going to call that X. Now, they told me R is a midpoint of TG. Remember, what a midpoint means is it splits it into two congruent pieces. So this piece and this piece are congruent. It's obviously not drawn to scale. So I'm going to call that piece X also. They didn't tell me what RG is, but I know it's got to have the same length as TR. The other chord in red, they told me that EI is 20 and IR is 4. EI, notice that's the whole thing. If that whole thing is 20 and I've already used up 4, then that means RE has to be 16 so that they add up to the full length. I spot 2 chords in this problem. Nothing is outside the circle. TG is one chord and IE is the other chord. So this is going to be the chord power theorem, which said if I take the 2 pieces in blue and multiply them together, it should equal the 2 pieces in red multiplied together. So I should get X times X, that's one chord, TG. And in red, the 2 pieces were 4 and 16. So I get X squared equals 64. And then to get rid of the square, I square root both sides. You technically get 2 answers. You get 8 and you get -8. However, -8 doesn't make sense because you're talking about the length of a segment, and length cannot be negative. So I only use X equals 8. And that's the length of TR. We called it X, and we just found X. That's 8. TR. The second one, let's first identify what is the problem being made up of, secants, tangents, or chords. In one color, it's like in one corner of the ring, we have the yellow secant segment that intersects the circle twice. And in the other corner, we have the blue segment, which is a secant that intersects the circle twice. Okay, I'm done with my announcer voice, sorry. Okay, so I've already decided this is going to be the secant power theorem because both of those segments hit the circle at 2 different points. Here's where it starts. So remember, what do you need for this? You need whole times outside equals whole times outside. So let's start with the yellow one. What is the length of the entire yellow one, the whole length? A lot of times people think about this too quickly and they multiply the 2 pieces together. But if you're taking total length, you've got to add these together. From here to here is 8, and from here to here is 2. So the whole length is 10. And then the outer piece is 2. So I'm just going to label that O. So there's my whole, there's my outside. For my blue one, the whole length from here to here is X, and then I add on 4 more units. So the whole thing is X plus 4, and the outer part is just 4. That's the part that stops at the circle and doesn't continue inside. So setting it up, whole times outside equals whole times outside. Let's start with the yellow one. We've got the whole piece was 10 times the outside part was 2. And then for the blue one, the whole thing was X plus 4, and the outer piece was 4. So this side turns into 20, and you can either distribute or you can divide by 4. I'm just going to distribute because there's no fractions in this one. So I just get 4x plus 16. You move the 16 over, you get 4 equals 4x. So x is equal to 1. Once you set it up, it's some algebra. So that one's 1. So again, I want to just clarify again, you don't want to multiply these pieces together when you're using the formula. Even though there's multiplication here, the whole length is going to be these 2 pieces added together. So we're not calling it 4x, we're calling it x plus 4. We're not calling this 16, we're calling it 10. Okay, the last one, you'll notice this piece is now just a tangent because it only hits the circle 1 time, and then if it was to continue, it would just go outside the circle. It wouldn't hit it again. So that's going to be labeled, I'm going to call it tan for tangent. And then the other one, let's use blue again. This is a secant segment because it hits the circle 1 point, 2 point. So for this one, since it's a secant tangent, it's whole times outside for the blue one because that's a secant. But whole times outside for the yellow one, it's the same thing. That's just going to be the tangent piece squared. Okay, so if I set this one up for the secant, let's label, the whole thing would be x, that's the part inside the circle, plus the 2 on the outside would be x plus 2, and then the outer part would just be 2. So there's my whole, there's my outside. So I'm going to set up, erase some of these dots. There we go. Whole times outside equals tangent piece squared. So I only have one secant this time, not 2. The whole piece was x plus 2. The outer part was 2, so 2 times x plus 2 equals, the tangent piece was 6, but I square it. So 6 squared. Distribute, or divide by 2, your choice. I'm going to do 2x plus 4 equals 36. Move the 4 over. 2x equals 32. Divide by 2. X equals 16. That's it. All they wanted was for you to find x. You don't have to plug anything back in because they didn't ask for it. Now I want to do one of them that is a little bit more involved, that has some overlapping segments, just to show you how to piece that together. And the writing gets a little bit laggy when I have too much ink on the page, so I am going to clear the ink. If you need something right now, you can pause the screen and write down what you need, but it's going away in 3, 2, 1. Oh no, where'd it go? Just kidding. All right. This one's a little bit challenging. Okay, so I'm going to walk you through this one. If you want to try and pause it, if you're up for a challenge, you want to try it yourself first, you can pause me and try it out. But you may get stumped at some point, and that's okay. I want to walk you through which part of the diagram do you start with. If you know where to start, the rest of the problem to finish isn't too bad. Okay? So I notice in this problem, I got a couple things going on. I definitely have a tangent segment going on right over here. I'm going to label that tan. And I've got a couple different secant segments. If you're looking from B to D, that would be a secant. And remember, I don't care about what happens after it hits the circle the second time. So B to D would be a secant. But if you're looking at the other side of the diagram, you actually have some more secants. EG is a secant. And from E to C is also a secant. Okay, so I'm just labeling some different parts of the diagram so you can see what we got going on. Now, where do you even start with a problem like this? Do you start on the side that's on the left that has the A's, the B's, the C's, and the D's, or do you start where we have the E's, the F's, and the G's? What I like about the left side of the diagram is that it only uses one letter. It only uses the letter X. If I look at this one and I look all the way from B to D at that secant, I'm only using the letter X, which means whatever equation I set up is only going to have one variable, which means I can solve. Whereas if I go to the other side of the diagram and I try to set up stuff, let's do it in blue. If I try to set up something, I guess green and blue. Here, it uses the letter Y, and then if I use from E to C, it uses the letter X. I'm going to have one equation that has two variables. No, I don't want to do that. Okay, so I'm just going to start with the left side of the diagram first. And what I'm going to focus on is the tangent that I labeled from A to B, and the secant that I labeled from B to D. So just the two segments in red. Okay, so part 1 deals with a tangent and a secant. So I'm going to use the tangent secant power theorem for this one. For the secant part, it's going to be the whole times the outside, and for the tangent part, it's just going to be the tan squared, because the whole and the outside are the same thing. So let's start with the secant. The whole secant, remember, starts at B and ends at D. I don't care about this part out here. That's not part of that secant segment that I care about. The whole length is 6 units to C plus another X units to D. So that's going to be X plus 6. And then the outside part is just 6. And the tangent piece is X plus 3. You have to square that whole quantity, so make sure you put parentheses around it. Left side's a little bit easier. I just distribute. So I get 6x plus 36. And this one I've got to FOIL out. Remember, this is x plus 3 times another copy of x plus 3. It is not x squared plus 9. It's x squared. Now I do the outer ones. 3 times x is 3x. Now I do the inner ones. 3 times x is 3x. And now I do the 3 times 3, which is 9. So 6x plus 36 equals x squared plus 6x plus 9. There's a 6x on both sides, so I can get rid of that. And I get 36 equals x squared plus 9. So it is quadratic. And I notice the exponent's 2. So I'm just going to subtract 9 from both sides and take my square root. So 25 equals x squared. Not 25, 27. Our brains always like to do that for some reason. 36 minus 9, we want it to be 25 because I think we want it to be a perfect square even though it's not. I do that time after time. Nice square root. We're going to leave this one in simplified radical form instead of using a decimal since the problem's not done yet. We still need to figure out what y is. They asked for x and they asked for y. So if I break that down, that would be rad 9 times rad 3, which would be 3 rad 3. Oops, fix my handwriting there. Okay. And obviously you would also get negative 3 rad 3 since you took a square root of both sides, but that doesn't make sense because if you plug in negative 3 rad 3 here and you add 3, it's going to be a negative result, right? Try it. Negative 3 rad 3 plus 3 is negative 2.1. That doesn't make sense for that tangent segment to be negative 2.1 units long. So I cross this one out. I know x is equal to 3 rad 3. So this one's 3 rad 3, which means this guy I can label now in the picture as 3 rad 3. So I'm done with the left side of the diagram. We could say goodbye to that. Now we're going to work our way towards the blue and green segments over here, and we're going to try to figure out what y is equal to. So now I'm dealing with a secant segment, GE, and another secant segment, EC. So this is going to be round 2. Now I'm dealing with secant power theorem. Doesn't matter which one I look at first. Let's just look at EG. It's whole times outside. The whole thing is y plus 7. E to f plus f to g. So I got y plus 7 times the outside part, the part that starts at E and ends at F, is just y. Equals, now I'm looking at the part in pink. The whole thing, this is where you got to use a little bit of radical algebra. This piece is 2 rad 3, plus the piece we just found for x was 3 rad 3. When you add radicals, you add the outside coefficients, and then you leave the radical the same. You don't make that rad 6, you just leave it as a rad 3. So this would be 5 rad 3. That's the whole thing. And then the outside piece is just the part that goes from E to D, which was 2 rad 3. Okay. So this side, we get y squared plus 7y. And on this side, when you multiply the rads, you just multiply the outside numbers, and then you multiply the inside ones together. 5 times 2 would be 10. Rad 3 times rad 3 is just normal 3. So 10 times 3. Y squared plus 7y equals 30. This time I can't use square roots to solve it because of the fact that I have a y term that's in the problem as well. It's not just x squareds and constants. There's an actual y term. So this one I'm either going to have to factor or use the quadratic formula. Regardless of which method I pick, I have to get 0 on one side. So I'm going to subtract 30 from both sides. Okay, so I got one side set equal to 0. The numbers are not very big, so I am going to try to factor it. What multiplies to negative 30? And what adds up to the middle term, which is 7. So what magic numbers are going to make that work? If the product is negative, I know one of them's positive, one of them's negative. 10 and 3. 10 times negative 3 would be negative 30. 10 plus a negative 3 would be positive 7. Since my lead coefficient here is a 1, means I can jump right to my parentheses sets. I don't have to group the problem. So this would be y plus 10. That was one of my magic numbers, and the other one was minus 3. Y minus 3. And now I use my zero product property to set up my two equations. Either y plus 10 needs to equal 0, or y minus 3 needs to equal 0. So this one would give me negative 10, and this one would give me 3. You know, sometimes you can keep both answers, but you need to check. This is a geometry problem. You're looking at length. Can this length from E to F right here, I'm circling in black, can that be negative? No. Length can be 0 or positive. It can't be negative. So I cross off the negative 10 and get y equals 3. So that'll do it for the power theorems. Sure, we're still recording. Good. So the last one I want to look at is a big circle problem. And we've seen these a little bit in 12.3, but they're a little bit bigger now because we have more angles and arc formulas to use. Okay. You do have a Google Form homework assignment that has one very similar to this. So I want to walk you through kind of how to approach it, and then you'll get some extra practice. I have some posted for you as well. The first thing you do is you look at the circle. Obviously, there's a lot of overlapping segments, and it looks kind of overwhelming. The biggest thing to remember with these problems is you need to just look at 2 segments at a time. And you don't want to look at the whole diagram or your eyes are going to play tricks on you. Focus on one angle at a time. Look at what segments are making up that angle and what arc is intercepted, or arcs. Okay? So let's look at the given information. They give you circle O. What does that tell you? Right away, that means that O is the center of the circle. That's what I know from that. They're telling me AB is a tangent segment. That's helpful. So this segment here from A to B is a tangent. Now, all the arc measures are expressed for the most part in terms of a variable, which we're going to have to solve for. BC, let's color code our arcs. BC in yellow is 2x minus 16. CD, let's do that in blue, is x plus 40. DE, let's do that in green. That is just good old x. And then EB is 60. Let's do that one in pink. Okay. So I got my arcs labeled. This one was 2x minus 16. This one was x plus 40. This one was x. And then this one in pink was 60. They gave me that one for free. Hey. Okay, so I got different colored arcs. The first thing you want to do in one of these big circle problems is figure out what all the arc measures are for the circle, because you can't get angle measures unless you know what arc measures are. All of the formulas we saw on the front page of these notes were related to angles and arcs. So the first thing you want to do is you want to set up an equation that you can use to help you figure out what the arcs of the circle end up being. What do all of the angle measures or all of the arc measures have to add up to in a full circle? 360. So the first thing we're going to do in this one is we're just going to add up all the arcs that I have in the different colors and set them equal to 360. So I get x plus 40 plus 2x minus, that's a bad 6, minus 16 plus 60. All of those have to equal 360. So 4x plus 84 equals 360. Move the 84 over. 4x is 276. Divide by 4. X is 69. Okay, that's x though. That doesn't tell you what the arc measures are yet. That means you have to plug them back in now. So if you plug in 69 for x for each of these arcs, 69 plus 40 tells me this one's 109. 2 times 69 minus 16, this one's 122. X is just x, so that one's 69. And the pink one we already had was 60. So, good way to check your work, add them up. They should all add up to 360. Now you can actually start attacking the problem and figuring out what the angle measures are. And nothing says you have to do them in order. If you want to solve for angle 12 at the beginning and you have the information to do it, by all means, solve for angle 12. Nothing says you have to go 1, 2, 3, 4, 5, 6. Go in whatever order you want if you have the information to do so. I'm going to try to go in order, though, just to be consistent here. So first one I'm going to focus my eyes on is angle 1, and I'm going to ignore the rest of the picture I don't care about. This is angles and arcs. We don't care about the power theorems. We care about the box from the front. What's the location of the vertex? So I look at angle 1 and I notice that the vertex is on the circle. I'm going to locate the vertex and I'm going to trace out the chords. One of them ends at C and one of them ends at B. So that intercepted arc is 122. Since angle 1 is inscribed to that circle, that means I take the arc measure and I divide it by 2. So angle 1 is just going to be half of that intercepted arc, which is CB. Half of 122 would be 61. So I got one angle knocked out for free, 61. Okay, angle 2. I notice angle 2's vertex is also at D, and it's on the circle. Inscribed angle, trace the arcs out. It intercepts the pink arc, ends at E, ends at B. That's 60 degrees. So just like the other one, since the vertex is on the circle, that angle has to be half the arc measure. So I'm going to take half of that pink arc, half of 60. Measure of angle 2, half of 60 would be 30. So angle 2, done. Okay. Angle 3 also has a vertex on the circle at E. I trace out this chord to D. I trace out this chord to C, and I ignore the rest of the picture. What arc did it intercept? It intersected D and C. So in between there was arc DC in blue. That's 109. So I'm going to cut it in half to go backwards to angle 3. Measure of angle 3 is 1/2 of 109, which would be 54.5. So this one over here in green, that's 54.5. Okay, angle 4, also inscribed. Here's angle 4. Vertex is on the circle. One of my chords goes all the way out to C. The other one goes out to B. So it's intercepting the yellow arc, CB, which was 122. So I'm going to cut it in half. Vertex is on the circle. Lots of inscribed angles so far. Half of 122 would be 61. So this one's 61. Angle 5, I locate is right here. Vertex of that angle is on the circle at B. Use the finger trick if you want. One chord is one finger goes out to E. Your other pointer finger is the other chord goes out to D. So it's intercepting the green arc, which was 69. So I'm going to cut 69 in half to go backwards to the inscribed angle. Measure of angle 5 is 1/2 of 69, which is 34.5. Okay. Let's look at angle 6. Angle 6, right here. This one is not inscribed, but the vertex is still on the circle, and it's made up of a tangent, and I know it's tangent because the problem told me tangent AB, and it's made up of a chord. Do that in green. EB is the chord. A tangent chord angle follows the same rule as an inscribed angle. The vertex is still on the circle, so I cut it in half. That intercepted arc in between the green chord and the red tangent is 60 degrees, so it's going to be half the measure of that arc, since the vertex is on the circle. Measure of angle 6 is 1/2 of the pink arc, which was 60. So this would be 30. Uh-oh. This is 30. All right, where's angle 7? It's like, where's Waldo? Okay, angle 7 you have to be careful with, because even though the vertex is on the circle at E, here's angle 7 in blue. The problem is this is not a tangent. Even though it hits the circle once, you have to look and notice that it keeps going. That's actually a full secant segment. This is not a tangent chord angle at 7. So how do I get around that? I don't have a formula for it if it's a tangent or if it's a secant and a chord. But you have to notice these two angles. I'm going to highlight them in yellow. This takes us all the way back to like September. These are supplementary. That's a linear pair. You already figured out that angle 4 was 61. So angle 7 is just the supplement. I'm going to subtract from 180. So measure of angle 7. Where do I want to go? Let's go to the bottom. Really uncalibrated. Measure of angle 7 is just going to be 180 minus angle 4 was 61. So that's 119. And all I'm using for that is the idea that it's a linear pair with angle 4. Can't cut that one in half because it's not inscribed and it's not a tangent chord. A secant and a chord doesn't quite follow the rule of cutting in half. All right, angle 8. Way out here, I notice the vertex is outside the circle. So I'm going to use my new rule for today. My outer arc, if I trace out the red one, ends at B. And if I trace out the blue one, it ends at C. So my outer arc is going to be BC, and my inner arc is going to be EB. I'm looking at the yellow one and the pink one. What do I do to get that outside angle? I do outside minus inside, and I divide by 2. The measure of angle, let's do some of these over here. Measure of angle 8 is going to be 1/2 the difference of those two arcs. The outside one was 122, and the inside one is 60. So 122 minus 60, and then cut it in half would be 31. Where's angle 9? Angle 9, I'm going to circle it in green. Notice it's not at the center. It's inside the circle, but the center is here at O. So what I'm going to do is I'm going to figure out what arcs are intercepted by angle 9 and the one across from it, angle 11. Angle 11 is intercepted by the blue arc, and angle 9 is intercepted by the pink arc. This one is very similar to the last one we just did, but instead of subtracting the arcs, we want to add them and divide by 2. I'm just averaging those two arc measures. So I'm going to add up 109 plus 60, and then I'm going to divide it by 2. The measure of angle 9 is 1/2 the blue arc plus the pink arc, 60 plus 109. And that's going to be 84.5. And that's actually angle 11 as well, so we can label both of those 84.5, 84.5. So we'll go to 10 first, but when we go to 11, we'll know we already solved it. And that's because they're vertical angles, right? Vertical angles have to be congruent. It takes us back to first semester. Angle 10, same idea. Now, you could just use the fact that you already know 9 and get the supplement. Those two right here form a linear pair. So that's one way you could do it. Or you could use the idea that the vertex is inside the circle, but not at the center again. This time, angle 10 is getting intercepted by the yellow arc, and the vertical angle across from it, 12, has the green arc it's intercepting. So I would just add the green arc and the yellow arc and divide by 2. So angle 10 goes with this one, angle 12 goes with this one. So 69 plus 122 divided by 2. So that one would be 95.5. I'm going to stop labeling them in the picture. It's going to get too complicated. Angle 11, we already said it's vertical to angle 9, so we already know angle 11 is also 84.5, just like angle 9. The more angles you solve, the quicker they get later on, because chances are it's going to be one of the same values you already found. Angle 12 is vertical to angle 10, and hey, we already found angle 10 was 95.5, so angle 12 also has to be 95.5. I just used vertical angles for that. You'll make a comment here. Vertical angle to angle 9. And this was a vertical angle to angle 10. Angle 13. Back to some easier ones. This one has a vertex on the circle and it's inscribed to the green arc. So you literally just look all the way across at the green. 69 divided by 2. So 1/2 of 69 would be 34.5. Angle 14. Where's 14 in the picture? There's 14. Vertex is on the circle. You trace it out. One of them stops at E, one of them stops at B. So I have an inscribed angle. Look at what's in between E and B. Get the pink arc is 60. You got to cut it in half since your vertex is on the circle for that inscribed angle. So angle 14 is 1/2 of 60. Which is 30. And we have come to the end of the race. Angle 15, there's the last one. Here's 15. Vertex is at B on the circle. Trace it out. B to C, B to D. You have an inscribed angle, and in between C and D is the blue arc, 109. So how do I go backwards? I cut it in half. So angle 15 would be 1/2 of 109, which would be 54.5. And that's it for that big circle problem. Again, don't look at the whole diagram at one time. Obviously, if you were to look at it right now, if you had no context to this video, this diagram would look horribly complicated. But I didn't draw all this at once. I did it piece by piece. Use your highlighters, use your colors, and focus your eyes on just 2 segments at a time, 1 angle at a time. If you focus on just 1 piece at a time, it's going to be a lot easier to solve these. Identify the location of the vertex. That's what it's about. Locate the vertex. Every time you're finding a new angle, you should be asking yourself, where is my vertex? Because what that's going to help you decide is which of the formulas from this chart to use. And again, look at the chart that I posted for you online. It's nice and organized. It has diagrams. It has some examples for you to help make these problems a little bit easier. That should do it. You got a practice worksheet, you got a Math Excel, and you've got a Google form to do. Happy solving angles, arcs, and segment lengths.